This video tutorial will introduce the concepts of logic gates and truth tables. Here we have the concept of two switches, X and Y. Electricity is running through them. We go through an AND gate and we come to an output, in this case a light bulb. If we allow the electricity to run through X and the electricity to run through Y, then we have light. So that's X and Y must be engaged for light. And this could be represented in a truth table as looking at all the eventual combinations between X and Y. 0 represents no power or off, and 1 represents power. If we have the switch on at X and on at Y, then in an AND we have a signal at the light. If we have no signal, if we have the switch off at X and off at Y, then the light is not on. If the switch is off on X but on on Y, we have no light. If the switch is on X and off on Y, we have no light. We only have light if switch X is on and switch Y is on. Then we have light. Another way of considering this is to say that we have X equals true, Y equals true, then the light is on, or equals true. The other type of gate we have is an OR gate. In an OR gate, we don't need both switches to be on, we only need one or the other to be on. So we have X or Y. If X and Y are off, then we have no light. If X or Y is on, then we will have light. If X is on, we have light. And if both are on, we have light. And this is represented as an OR gate. We have a true signal here, so the light is on. We have a true signal here, so the light is on. And when this is off and this is on, we have the light on. The only condition where the light is off is when both of these are set to off. This is an OR gate. We have an exclusive OR gate, which is similar to this, except that when X is on, the light is on, and if Y is on, then the light is on. But if both are on, the light is not on. Whereas within an OR gate, if both of them are on, the light will be on. This one has to be one or the other, but not both. And if both are off, the light is not on. So this is an OR gate and an XOR gate. And they're represented in the truth table as OR 0, 1, 1, 1, and exclusive OR 0, 1, 1, 0. And we always represent two variables, X and Y, or A and B, as starting off 0, 0, 1, 1, 0, 1, 0, 1. And this covers all of the possible combinations of these two variables. So we have AND, OR, exclusive OR. We also have the concept of not X or not Y. And we represent this here. If we have 0 here, we have a 1 here. Off here equals on here. If we have an on here, it's represented as an off here. So it is the opposite of the value of X or Y. If we look at this in the truth table, we see that not X is the opposite of whatever X is. X is 0, 0, 1, 1. Not X is 1, 1, 0, 0. Not Y, if Y is 0, 1, 0, 1 in this case, then we have 1, 0, 1, 0. So not is the inverse or the opposite of the variable that we're looking at. We also have the concept of NAND and NOR. NAND and NOR is the same as taking an AND and putting a NOT after it. So we're taking the opposite of an AND, and a NOR is the opposite of an OR. So if we take an AND as being 0, 0, 1, then a NAND is 1, 1, 1, 0. And here we have a NAND gate. It's similar to an AND, except it has the circle after it. This doesn't have the circle. And this is logically similar to an AND followed by a NOT. And this is NAND. So it's the opposite. If both X and Y are off, then we have a signal. If either is on, if both are on, then we have no signal. Thank you.